Hi friends, in this video let's discuss about synchronous motor at no load without losses, at no load with losses. So generally in synchronous motor, for example, this is my supply voltage V. When the supply voltage is given to the motor, I said you already, in every motor generator action will take place which produces the EMF which is in opposite direction to the supply voltage, which is in opposite direction of my supply voltage, nothing but here my EMF which is called back EMF. At no load condition and there is no any losses, this V is exactly equals to EB and the load angle is 0 because no load condition actually the load angle is 0. These two are exactly 180 degrees to each other. This is ideal case, but practically even at no load condition some losses are there. Yes or no? So at no load with losses. For example, this is my supply voltage V. Actually, ideal case, the back EMF should be here. But due to some losses, back EMF is actually here. This is my back EMF. And this angle is called load angle delta, very small. This delta is a small angle at no load condition. This is the back EMF and this is the voltage at no load but with some losses. So what is the resultant of these two? For example, if you take a resultant like this is the resultant value, for example ER. See here, at no load condition without losses, actually the back EMF EB is equals to V minus IAZS. Without losses, that's why IA is equals to 0. If IA is equals to 0, the back EMF is equals to V. This is the process here. But here, even under no load condition, but small current is flowing through the winding, which leads to small losses. So here, the back EMF is equals to V minus IAZS. Here, let's see, EB, V, this is opposite to each other, right? So V minus EB is equals to IAZS, the sum of EB and V. These two are vector sum but in opposite direction. That's why this is IAZS. Nothing but the vector sum is ER. This ER is equals to IAZS. If resistance is neglected, IAXS. This is the vector diagram of synchronous motor at no load condition with losses. The losses due to small current, that's why IAZS and IAXS. For example, armature resistance is 0, IAXS. So this ER is nothing but IAXS or ZS, whatever. This is at no load with losses. Now take the same vector diagram for loaded condition. Loaded nothing but sir, resistive load or inductive load or capacitive load. Draw the vector diagram for all the loads. Are you okay? So draw it. Hold the video, draw the vector diagram for all the loads. Come on to it. Okay, come on. S. Loaded synchronous motor. For example, I will give you case 1. Remaining you have to draw. Case 1. lagging load. I am drawing for lagging load. See here, synchronous motor at lagging load. Nothing but lagging load, nothing but magnetizing or demagnetizing. Synchronous motor, lagging load, nothing but magnetization only. Magnetization, nothing but overexcited or underexcited. Exactly, underexcited only. Underexcited, nothing but what is EMF? The EMF is should be less than V. Underexcited. That's why excitation is less. That's why E less than V. Are you okay? Right? So here let's draw the vector diagram. This is voltage V. Are you okay? Right? Next, this is EMF E. Of course, this EMF is less than V, and this angle is delta, load angle delta. And the resultant of this EMF, of course this is back EMF, resultant of back EMF and V is ER. So let's see, this is actually less value, and this V actually more value, right? V actually more value, EB actually less value, like this. This is our ER. This ER is equals to IAZS only, right? So here, for example, I said you lagging, nothing but my armature current is lagging to the voltage. This is the angle is called power factor angle phi, and this is the angle is called the angle between IAZS and IA, nothing but Z, nothing but theta, impedance angle. What is here? Here the angle between V comma IA is the power factor angle phi. The angle between IAZS and I is taken as impedance angle theta. Now can you tell me the angle between ER and V? Do it fast. Yeah, tell me. Yes, very good. Actually, I want this angle when the total angle is theta and this angle is phi. So this angle is theta minus phi. So what is the angle here? Theta minus phi is the angle between these two. This is for lagging load. Let's go for leading load. Case 2. Case 2 is the leading load. For leading load, the armature reaction is demagnetization. Of course, nothing but overexcitation. Nothing but the EMF value is greater than the supply voltage, the back EMF mostly, because of overexcited condition. It is possible. And draw here, for example, this is my supply voltage V. The back EMF should be greater than the supply voltage here, and here the angle is the delta. Overexcited, delta is more, and the resultant is what is this? This is ER. ER is equals to IAZS, of course we know that, and this is the leading load, so my armature current is here, and the angle between V and IA is the power factor angle phi, and the angle between IAZS and IA is the theta. Now can you tell me what is the angle between ER and V? ER and V is nothing but this much of angle. this much of angle is nothing but theta plus phi. Here theta minus phi and here theta plus phi. Simply, the angle between ER and V is theta plus or minus theta plus or minus phi, plus for lagging load and minus for leading load. This is very, very important. You should remember. Okay. Case 1, case 2. I want to go for case 3. See here, is it okay? Case 3. Unity power factor load. Nothing but resistive load. Nothing but here normal excitation and cross magnetization. Nothing but mostly in this case the EMF is nearly equals to V. So let's draw the diagram. This is my voltage V and this is my back EMF EB. Mostly the angle, load angle is very less, actually delta, and mostly these two are same in magnitude. When these two are same in magnitude, then the vector diagram is like this. See, this is our ER, where ER is equals to again IAZS, there is no any change. And I said you this is unity power factor, nothing but my armature current is, my current is in phase with voltage. If the angle is 0, then only it is called unity power factor, nothing but the voltage and currents are in phase to each other. When phi is 0 and the angle between IAZS and IA is the theta, now the angle between ER and V is equals to theta. These are the vector diagrams of synchronous motor under loaded condition. Are you okay? Alright, these are very important. From these vector diagrams, here we have a small formulas. Those formulas I will give you for lagging. You have to draw for leading load also. That's why I removed this leading load. So I will draw for lagging load. Let's see here. If this is EB, this is also EB. If this is V, this is also V. Because in parallelogram parallels from this, the EB is the vector sum of ER and V. EB is the vector sum of ER and V. Nothing but EB is equals to square root of ER square plus V square, ER square plus V square minus 2 ER V cos theta. What is cos theta here? Here theta between ER and V is theta minus phi. So this is EB. Tell me what is EB? EB is equals to square root of ER square plus V square minus 2 ERV cos of theta minus phi. Here theta minus phi for lagging and theta plus phi for leading. Are you okay? Here theta minus phi for lagging load and plus phi for leading load, and for unity power factor this value only theta, because for unity power factor the power factor angle is 0 degrees. You should remember this formula. This is also important from the vector diagrams I given you for lagging, leading and unity power factors. This is very important for synchronous machine. Okay, so next one. Again, we have a small formulas. Let's see here. From this, I will draw for lagging. You have to derive for leading and unity power factor also. Let's see, from the sign rules, we have some sign rules. From that sign rules, see here, this is EB, right? So EB upon what is the angle opposite to EB? Opposite to EB is theta minus phi. EB upon sine of theta minus phi is equals to this side by sine theta is equals to this side by sine theta. What is this side? This side is ER. What is this side? This side is ER. What is the angle here? Can you tell me? If this is the delta, this is also delta. Yes or no? If this is the delta and this is also delta. Exactly, because of parallel. So tell me, what is here? This is ER. So ER upon, what is this angle? Delta, sine delta. This is the formula for lagging load. For example, if it is leading load, here is the plus. For example, here minus for lagging and plus for leading again, and for unity power factor, the power factor angle is equals to 0. Again, the formula is the same for all lagging, leading and unity power factors. Synchronous motor at loaded condition. These the formulas you should remember. What is here? This is EB. EB upon sine theta. Because phi is equal to 0, EB upon sine theta. And ER upon, what is the angle? This one? Delta. ER upon delta. So these are, you have to remember. Are you okay? Are you okay or not? Right. It's completed. Let's go for another power equation derivation from this sign rules. Okay, let's derive the power equation from this sign rules. P is equal to EV by X sine delta. I will derive that power from these equations also. Okay, let's see. Let's see here. The power in generally, power P is equals to VI cos pi. We know that. So, power P is equals to VI, nothing but IA. We know that IA ZS is equals to ER, then IA is equals to ER by ZS. V ER upon ZS and cos pi. Okay, so tell me, P is equals to V and ER. From this equation, ER is equals to EB sine delta upon sine of theta minus or plus phi into cos pi is there and ZS is there. This is the power equation. Sir, what you derived, sir? Where is our power equation? Just wait. For example, see here, if armature resistance neglected, are you okay? When armature resistance neglected, ZS is equal to XS. When ZS is equals to XS, theta is equals to 90 degrees. So now substitute all these values, you can get the power equation. Come on. So P is equals to, are you okay? So V into EB or EB into V upon ZS is equals to XS, and sine delta is there, sine delta, and cos pi is there, cos pi upon sine of 90 plus or minus 5. 90 minus 5 nothing but first quadrant. 90 plus 5 nothing but second quadrant. Wherever you go in first quadrant and second quadrant, in both the cases sign is positive. So sine of 90 nothing but cos pi. So cos pi gets cancelled out. So what is the power? Power is equals to EBV upon XS sine delta. This is our power equation. Is it clear? Are you okay? Right? So this is our power equation of synchronous motor. We derived already in different manner, but this is in different manner by using this vector diagrams. This is very important analysis. Okay? So now the synchronous motor at no load and loaded conditions is completed. Are you okay? Thank you.